All right. So so as the title suggests, I'm going to talk about two-terminal charge tunneling, which we are calling a sanity check for Majorana zero. Now, some of these, the material that I'm going to talk about is still being written up. My collaborators have been Christopher Moore, who is my graduate student at Clemson, and Theodore Stanescu, who is a long-term collaborator since my Maryland days. All right. So this is a brief outline of the talk. Since I take it there's going to be a fair number of graduate students and postdocs, I'm going to start with a very brief introduction to Majorana zero modes, and also because this is a conference or school not specifically geared to Majorana zero modes, so I'll give a little bit of introduction. Then I'll come to the main part of the talk, which is Majorana bound states in non-homogeneous or inhomogeneous systems. By that I mean some position-dependent potentials and what sort of complications they might bring in. Those of you who are aware of the experiments, they know that there are a fair number of gates that are used in back gates that are used in these experiments. So they could very easily create position-dependent potentials. So we'll look into that, and we'll see what kind of complications they might bring in. And then I'll talk about the two-terminal charge tunneling, which we are going to propose in a few more days as a sanity check for Majorana zero modes. By that I mean whether or not the zero bias peaks that people are observing are really due to Majorana zero modes or some other spurious zero energy states. All right, so it's a very brief introduction. Majorana zero modes, in the order of increasing simplicity, I have listed from top to bottom. In 1991, Moore and Reed, in their famous paper, they first talked about Majorana Fermions in the context of condensed matter in the 5-half fractional quantum Hall state. And then Reed and Green, they connected the physics of 5-half state to the chiral POF, spinless chiral POF superfluid or superconductor state in 2D. Kitaev went from 2D to 1D, still spinless POF superconductor. But of course, spinless POF superconductors are not available in the lab. So one way to realize the same physics was proposed by Fu and Ken by proposing to build a heterostructure between a topological insulator surface and an S-wave superconductor. And then we further simplified the proposed structure, or further simplified the scheme to somehow create an analog of a spinless chiral POF superconductor in the lab. And that consists of, our scheme consisted of a semiconductor superconductor heterostructure, which could be in 2D or 1. This is where, the last one is where most of the experiments are on. So that's what I'm going to focus on. So this is the proposed setup. First, just look at the white box. The proposal is we have a semiconductor, and the semiconductor has strong spin-orbit coupling. That's the assumption. And suppose we proximity induce superconductivity, just simple S-wave superconductivity on the semiconductor. So now the spins in the semiconductor, which are spin-orbit coupled, they will also have S-wave superconductivity. And the only other thing we need is a Zeeman coupling. And in 2D, it's more useful to produce the Zeeman coupling by another proximity effect from a magnetic insulator. But in 1D, you can simplify that and produce the Zeeman coupling by applying a magnetic field which is parallel to the nanowire. So that's the proposed structure. And the idea is that if you have a 2D semiconductor film or a 1D nanowire, put it on top of a parent superconductor that produces superconductivity in the nanowire, and then place this entire system in the presence of a magnetic field which is parallel to the nanowire. Then above a certain critical magnetic field, zero energy Majorana bound state, or Majorana zero mode is the more precise term, Majorana zero mode a non-degenerate Majorana zero mode, which is a topological excitation, which has non-abelian statistics, topological quantum computation, and so on and so forth, that you may have heard about. It will appear above a critical Zeeman field. And one signature of its appearance is going to be if you can do a tunneling conductance measurement to the end of the nanowire, then you're going to see a zero bias peak. So the critical magnetic field is actually important here from my talk. So the critical magnetic field or critical Zeeman field, V Zeeman, has to be greater than square root of delta square plus mu square, where delta is the proximity induced superconducting gap in the nanowire. And mu is the chemical potential in the nanowire. By that I mean it's the chemical potential measured from the bottom of the band. So it's from here. So this is mu. All right. So so here I have summarized everything that I said so far. So we have to create an analog of 2D spinless PF superconductor or 1D spinless PF superconductor, and you can have a superconductor semiconductor heterostructure in 2D or in 1D. It's the same physics. You know, apply a Zeeman field, and those of you who are not 100% familiar with what is going on here, so the nanowire electrons, have strong spin-orbit coupling, and because of that, their band structure is going to be given by the two shifted parabolas. It's very well-known band structure of spin or electrons in the presence of spin-orbit coupling. And then you apply a Zeeman field which creates a gap at k equal to 0. Then somehow you have to manage to constrain your chemical potential within the gap. And if you can manage to do that, then you are done. So that's the reason why you need a critical Zeeman field, because your critical Zeeman field, because your Zeeman field has to create a gap which is larger than your mu. And the moment you get that, then you have a single Fermi surface, which is actually needed, one of the conditions for getting a Majorana Fermion or Majorana zero mode. So all of these physics of spin-orbit coupling, Zeeman field, and S-wave superconductivity, they conspire. So they are tabulated in this Hamiltonian. So it's a kinetic energy, chemical potential, spin-orbit coupling, Zeeman field, and S-wave superconductivity. So they conspire to give you Majorana zero mode above a critical Zeeman field, which, if you look at this equation carefully, you see the limit of delta goes to 0, which is where this curve is, it applies. Then this is simply Vz is greater than mod mu, which means the chemical potential is in the gap. All right. So here's the proposed setup or schematic. So you have a superconductor, and so you have a nanowire, and you put it in contact with a superconductor, and you have multiple gates. The gates do two things. The gates produce a strong barrier potential so that you can actually resolve if there's a zero bias peak by producing a gap or any other bias. And then gates also help you control the chemical potential. I mean, you hope to be able to control the chemical potential in the nanowire by having these multiple gates. And then you apply the Zeeman field, and above a certain critical Zeeman field, the idea is this Majorana Fermion or Majorana zero mode is created, and which you can probe by doing tunneling measurements. This is the theoretical prediction that we made some 5 years ago or 6 years ago. So this is the y-axis is differential conductance, DIDV. The x-axis is the bias voltage between the lead, metallic lead, and the nanowire. And as you can see, and the various cuts. Various curves are cuts at different magnetic fields or different Zeeman field. As you go on increasing the Zeeman field, the quasi-particle gap in the superconductor. So this is now a superconductor because the superconductivity has been proximity induced in the nanowire. So the quasi-particle gap collapses. That's the critical magnetic field, and above that critical magnetic field, you get a zero bias peak. You're supposed to get a zero bias peak, and that's your Majorana zero. This is the first experiment, the most famous one by Maurik et al. That came up right after this was the scheme was proposed. And as you can see, this is very similar to, well, I mean, there are differences, but at least in one respect it's very similar, which is above a certain Zeeman field. Again, the cuts are very different Zeeman fields. They do see a zero bias peak coming up, which is robust to further increase in the magnetic field. That's important, because zero bias peaks you can get in superconductors, but those are normally not robust to magnetic fields. Here, if it's a Majorana zero mode, then it's going to be robust to magnetic field, which is what they get for a fair range of the magnetic field. So that made people. There are other issues with this experiment. For instance, the gap does not collapse and so on and so forth, but I'm not going to talk about those. Basically, this is where the field was until. So these are the predictions. One is supposed to see these are the experimental results. So one saw fractional, which is 0.1 times 2 squared by h, and sharp zero bias peak, clearly separated from the gap. Ideally, it should be 2 squared by h if it's a Majorana zero mode. They saw a fraction of that. But that can happen because of other effects like temperature and barrier potential and so on and so forth. Importantly, they found the peak only above a finite B, which is very unusual in a superconductor. They found the peak robust against further increase of B, which is also unusual, but it's consistent with the Majorana zero mode picture, or consistent with the topological superconducting phase above this. So this is the topological superconducting phase. This is the trivial superconducting phase. All right. So right after these experiments were published, several groups wrote alternative scenarios in which one can have zero bias peaks, quasi-robust. They have various ingredients for producing independent of having a Majorana zero modes. Disorder, for instance, is one. I'm not going to talk about those as well. All right, so this is where the experiments and theory stood up until like 2 years back, or 3 years back. So experimentally, they found zero bias conductance peak above a critical Zeeman field, which is consistent with theory if mu equal to 0. The chemical potential is 0. Zero bias peak goes away for critical angles of the field. By that I mean, so you're applying a Zeeman field along the axis of the wire, but you can rotate the Zeeman field, and the theory is if the angle between the Zeeman field and the wire axis is greater than a certain value, then the zero bias peak is going to go away if it's from Majorana zero mode, which is what happens in experiments. So that's consistent with theory. They did not find any convincing feature for gap closure at TQPT. Convincing. Some experiments did claim to have seen some gap closure feature. That's also consistent if you have mu goes to 0, which is something that we showed right after these experiments came up. All right, but it's still not a smoking gun because there are other alternative scenarios which will produce basically similar features. Mostly due to disorder. Okay, so before I get into the new stuff, let me define a few quantities which will be helpful for us. One is topological degeneracy of Majorana zero modes. This is the basic operating formula for second quantized Majorana operator, and it's a Hermitian operator. So gamma dagger equal to gamma, which is very different from electronic second quantized operator where you have C and C dagger. Which are not, of course, equal to each other. But then you can see that if you have a conventional fermion, you have two operators C and C dagger, the creation and the annihilation operators. But you can take a certain linear combination of them and you can create two operators which are indeed Hermitian. So you have gamma 1 and gamma 2. And this is the inverse transformation, and you can write C and C dagger as that. So that basically tells you that you can view a conventional Dirac fermion as a linear superposition of two Majorana fermions. It's just a change of basis. Instead of calling the operators C and C dagger, we call them gamma 1 and gamma 2. But these gamma 1 and gamma 2, these Majorana fermions are tightly bound spatially onto the same Dirac fermion. So the question is, can you physically, spatially separate them? And suppose you do that, suppose you can, according to one of these schemes, the semiconductor heterostructure, if you could somehow spatially separate them, and let's say they are localized at two ends of a wire or some system, you can do the similar transformation and you can create a conventional fermionic state out of two spatially separated Majorana fermionic states. It's just plain same algebra as here. But now this conventional fermionic state, which is at zero energy, because Majorana fermionic states or Majorana zero modes are also at zero energy. So it's a linear superposition of two zero energy states, which is a zero energy state. And that conventional fermionic state can be filled or empty or filled. Those states will have the same energy. It's a topological degeneracy and so on and so forth. I'm not going to talk too much about that, but this is the basic property that's going to use, that is proposed to be used in topological quantum computation, non-abelian statistics, so on and so forth. The point that I want to drive home here is that a single Dirac fermion state, conventional fermion state, can be viewed as a superposition of two Majorana fermionic or Majorana zero modes. Just as two spatially separated Majorana zero modes can be combined or can be viewed as a single conventional fermionic state. All right, so you can use that picture of two spatially separated Majorana zero modes giving you a conventional fermionic state CC dagger. You can use that picture to devise some sort of a thought experiment, let's say, where you inject introduce an electron into the wire from one quantum dot, and it's going to be carried by the C state, which is a conventional fermionic state. That's the only fermionic state really that's available here. The electron cannot be localized by a Majorana fermionic state. It has to go into the fermionic state. And then you can, in principle, take it out from the other quantum dot, and that will produce a channel through which charge can flow in a topological superconductor like this. Now there are three ways charge can flow in a topological superconductor with Majorana fermion. The most dominant way is, of course, through local Andreev reflection process. So this is a zero energy Bogoliubov state, a Majorana zero mode. What is Andreev tunneling? Those of you a graduate student or postdoc, Andreev tunneling is a process that occurs at the intersection between a normal metal and a superconductor. You don't need any topological superconductor here, just a regular superconductor. The charge flows through such a junction only by this process, which is you have an electron come at the intersection, gets reflected as a whole, and because of the charge conservation, you inject or introduce a Cooper pair into the superconductor. That's actually the only process that will carry current from a normal metal to a superconductor. Because remember, the superconductor has a gap to single electronic excitations, so therefore cannot allow a single electron inside it. All right, the second process, if you can somehow manage to suppress this local Andreev reflection, which, remember, introduces two electrons into the system. So maybe you can play with your charging energy in the superconductor to exclude the two electron case, and then you can reveal this process. This is a single electron transfer process. And that's we call Majorana assisted electron transfer, sometimes also called teleportation. And then, of course, if you have a local Andreev process, you can also have a crossed Andreev process where the electron comes from this side, the whole gets reflected not from here but from here, and in the process you inject two electrons into the superconductor. These are three processes, and in most cases the first one which is going to dominate. If you want to see the second one, then you have to somehow suppress the first one. These are typical schematic experimental setups I have just taken from various papers. This is the first one from Morick et al. You have the nanowire, you have a superconductor on top, simple ASF superconductor, you have a metallic lid, and you have a number of gates that not only give you a huge barrier potential here, but also control the number of electrons. This is basically the same setup here. I'm showing you multiple times because I want to emphasize on the existence of these gates in all of these experiments. In fact, in experiments, they play around with the gate potentials a lot before they find the sweet spot of the gate potentials at which they find a zero bias conductance peak at the ends. So the gate potentials are important. So now let me come to the inhomogeneous background potentials. All right, so remember we have a multiple gate potential in the system, and they are of course introducing various electrostatic profile which you don't really know what they are. That's what we mean by inhomogeneous potential, background potential. Okay, so this is the ideal situation. You have a clean nanowire. As I just described earlier, you introduce the Zeeman field, V Zeeman. I'm going to also call it gamma in some of the later slides. So as you go on increasing the Zeeman field, then above a critical Zeeman field, you will enter into the topological superconducting phase. That's the theory. And in the clean system, in the ideal world, in the topological superconducting phase, you're going to produce two nicely well-separated, non-degenerate Majorana zero modes confined to the ends. That's the ideal situation. In real life, of course, even if you have a trivial superconductor, you know that, and this is something that is well known for the last 15, 20 years. Even if you have a trivial superconductor, if you have a potential in the trivial superconductor, you know that the potential traps quasi-particle states. These are called Andreev bound states. Not Andreev reflection, but Andreev bound states. So it's as if the electron inside these potentials, they are getting Andreev reflected multiple times at the intersection, and then by that process they are being trapped. And usually such Andreev bound states have subgap energies. Their energies are less than delta. But you can tune those energies. You can, again, none of this is topological. This is well known for the last 15, 20, 25 years. There are reviews of modern physics written on this. So you can tune the energies of these subgap Andreev bound states trapped by potentials in superconductors, and the energies will come to zero at a certain Zeeman field. Okay, you apply a Zeeman field, will come to zero, but they will not stay at zero if you further increase the Zeeman. So that's what I meant by the zero bias peak that they saw in the experiments. They remain stuck to zero energy for further increase of the field. These states will not, the energies will not stay at zero. So these are quickly unstable. But these states are conventional fermionic states. These are Andreev bound states, nothing to do with Majorana or topological. These are conventional Andreev states, very well known. But on the other hand, you know if you have a conventional Andreev states or conventional fermionic states trapped by some potential, you can view that as a superposition of two Majorana bound states, okay, as I just described earlier. But the two Majorana bound states are tightly bound, sitting on top of each other, and therefore, if you perturb the system from the fine-tuned point, there's going to be a matrix element coupling the two Andreev bound states, and the matrix element is going to perturb the energy away from zero. That's the physics there. All right. But what if I have in the system an Andreev bound state where the component Majorana bound states are not exactly sitting on top of each other, but somewhat physically or spatially separate. So they are kind of weakly coupled. Okay? They are very different from the topological Majorana zero modes. I'm going to call the topological Majorana zero modes, which are the two non-degenerate Majorana zero modes that appear at the two ends of a nanowire in the topological phase for Zeeman field greater than square root delta square plus mu square. Those I'm going to call Majorana zero modes. These I'm going to call Majorana bound states. They are just component states of an Andreev bound states, but of an Andreev bound state, but instead of sitting on top of each other, I have somewhat physically or spatially separated. Okay, so if I could do that, then you can. So that's the whole talk. So that can happen not when the potential is like a spike or a dip, but if the potential is physically, spatially spread out. If you have a gradient of the potential, then you can do this. You can have this. You can think of that. You can think of that, but you can also call these as the gate potentials, which are, and we'll come into that. All right, so this is a typical calculation that that one can do. I can have a spread out potential. I'm going to show some pictures of the potential, and I can calculate the spectrum as a function of Zeeman field. It might be that there are all sorts of states, higher energy states, but there is a branch, the lowest energy branch comes to zero energy and gets stuck at zero energy with some small splitting. This is going to occur, this is going to happen when the component Majorana bound states of an Andreev bound state are somewhat physically or spatially separate. This is the typical spectrum that you will find in that case. Very different from Majorana zero modes, not topological. If you move these Andreev bound states, you're not going to see topological non-abelian statistics or topological quantum or any of those nice things. These are basically Andreev bound states, where the component states are have been somewhat played with. All right, so this is a sketch of non-inhomogeneous potential. So let's say it's constant here. At the ends, it goes up, and it has to, because you know that at the end of at the junction of the nanowire and the metallic lead, which is here, there's a barrier potential. So the potential has to go up like this. Okay, this is and that's the chemical potential. You can calculate the same spectrum that that I was talking about earlier. This is the point in Zeeman field. Now I'm going to call gamma as the Zeeman field or Zeeman energy. This is the point where there is a topological phase transition, as you can clearly tell, because the bulk quasi-particle gap is closing here. But notice for that chemical potential, or for that kind of a background potential, there is a low energy branch that comes to zero energy much before where the actual topological quantum phase transition happens. This is where we expect to see nice, physically, spatially well separated Majorana zero mode. This is some other zero mode, which is of the kind that I was talking about before, Andreev bound state that is trapped. Now, now why is this robust? Again, this is, yes. You have a potential here, and the potential is the analog of your normal metal. I'm going to show the wave functions. Let me just tell you, the Andreev bound states are here. So when you talk about the superconductor, normal metal superconductor setup, and the Andreev bound states is confined to the normal metal region, that's precisely what this is. So that's basically applying a potential in the superconductor so that you have gone all the way to killing delta and making it a normal metal. Okay? But you can still have bound states even when it's not perfectly normal, but it's just a potential in the superconductor. And this, well, you can think of it as a normal. It's like a vortex in a superconductor which will have these Andreev bound states. So we can think of it as a normal metal inside the vortex, which has this Andreev bound states. Okay, but these Andreev bound states are important here because these are robust to further increase of the Zeeman. And the reason they're robust is because this is what has happened here, as I'm going to show by explicit calculation of the Majorana wave or the wave function of the Bogoliubov region wave functions. This is there. Again, this is the same potential profile here. As you can see, for gamma, and this corresponds to that. For gamma equal to 0.5 delta, which is over here, you have the subgap Andreev bound states, which is this. Okay, that's the wave function. This is the actual result of a calculation of a Bogoliubov region Hamilton. So it's just exact diagonalization of the Hamilton. Then you go on increasing the Zeeman field, you are in this situation. And notice here at 1.5 delta, which is right around here, the two Majorana zero modes have physically or spatially separated a little bit. That's where the energy of this Andreev bound state has come down to 0. And then since they are spatially separated, further increase of the Zeeman field or in fact any other perturbation will be unable to couple them strongly. And therefore, their energies are going to get stuck to 0. This is now, this is around 2.7. This is what happens around 2.7 and above. Above 2.7 delta, gamma greater than or gamma equal to 3 delta, this is the topological feature, the topological regime, where you have Majorana bound states at the two ends. This is an Andreev bound state where the Majorana components have spatially separated. This is useless. This is useful. Okay? Earlier result, if you take the local potential perfectly local, like a delta function, then also you can show that this is G inverse is basically the Zeeman field. Then you can also show, is from this paper, you can show that the energies of these Andreev states trapped by the local potential, delta function potential, they come to 0 energy, but they are fine-tuned. They increase the Zeeman field and it goes to. But this, for the perfectly local potential, they found this to be happening only in the topological side. We find that if you spread out the potential a little bit, not exactly delta function, but you give it a weight, delta V. So let's take, how much time do I have? This is a 45-minute talk. 5 more minutes to 45 minutes? Okay. All right, so I'm going to speed up now. These are 3 different potential profiles. One is somewhat local, one is more spread out, and the other one, the last one is, the width is almost the length of the wire, which is 2 micrometer here. And you can plot the spectrum as a function of Zeeman field. When it is, the delta V is 0.2, you have this fine-tuned 0 energy state at this value of Zeeman field. But on the other hand, when delta V is spread out, then you can see there's a wide range where you have almost or nearly 0 energy states. Remember, this point is on the non-topological side, because this is where the topological phase transition is happening here. And this is the Majorana zero modes. Over here, this is where the topological phase transition is happening, because that's the minimum of the quasi-particle gap. Okay? It's not going to be exactly come to 0 because it's a finite system. But you can look at the topological quantum phase transition by looking at the minimum of the quasi-particle gap, but that's here. But there's a wide range in the non-topological side where you have this quasi-robust 0 energy state. Again, so these are the special, so this is what corresponds to the situation that I'm talking about. You have a pair of Majorana bound states, which is really one blob of Andreev bound state here, and another pair, which is another blob of Andreev bound state here. Okay? And in this situation, the corresponding Andreev bound state is very robust. I mean, very is a qualitative term, but it's robust. Various different other, here we have plotted with the strength of the potential. The strength of the potential, we don't need it to be a lot. As long as it's the strength of the potential, many people talk about the strength of the potential, but is there really that much variation of the potential? We only need strength of the potential to vary of the order of the induced delta, which is in these experiments of the order of 0.25 millielectron. And here we are talking about gate potentials, which is producing potential of the order of electron volts. All right, it turns out you can do all sorts of local tunneling measurements. This is differential conductance, bias potential for single lead. You're going to see, so this is the crossover regime, which we call crossover regime, or the non-topological regime, where you have these robust Andreev bound states. And there is virtually no difference in the local tunneling conductivity between this and that. You can do spin resolved tunneling, and you're going to see no difference between this region and that. These are again various cuts at different magnetic fields. There's no difference between these and that. Let me quickly, okay, and this is the 2-terminal Majorana assisted electron transfer process, the teleportation. This nice calculation done by my graduate student, Christopher Moore. And as you can see, in the very recent 2016 Nature paper, Charlie Marcus's group claimed to have seen such teleportation amplitudes in some similar semiconductor superconductor hybrid structure. Unfortunately, we can show very similar. So this is the teleportation amplitude or the zero bias, two-terminal zero bias conductance. This is two-terminal zero bias conductance as a function of Zeeman field at various source drain bias. And this is the zero bias peak that's expected in the topological regime. And this is what they claim to have seen in Charlie Marcus experiment. Unfortunately, you're going to see the same structure, similar zero bias peak, also due to these robust unconstants. Much before there's a topological phase transition and there's a real topological. All right, so very quickly, the unpublished, still unpublished results. So what do you do? How do you differentiate? We have seen that the local charge tunneling, local spin tunneling, or even two-terminal teleportation type experiment, it's not going to differentiate between these robust unreal states and the real Majorana zero. So what do you do? So this is the problem so far. With inhomogeneous potentials, low or nearly zero energy, robust unreal bound states near the ends are quite generic. In this much more recent paper, this came out like a month ago, or 2 months ago, the Maryland group got very similar results doing different calculations, different types of calculations, but the conclusions are the same. And the reason they are robust is because they occur as overlapping pairs of Majorana bound states, and they are confined to segments near both ends of the wire, and they are useless for non-event statistics, TQC and all that. So no local measurement, one-terminal charge or spin tunneling, or even two-terminal teleportation like experiment can differentiate between. How about a little bit more difficult? Let me skip over this. This is an Arnaud-Bohm type experiment that was proposed by these guys, and this was billed as this anti-correlation in conductance. It's written here, study as a function of flux, provides a unique signature of Majorana bound state which cannot be faked by an unreal bound state. So the basic thing is this anti-correlation between currents, red and blue. I'm not explaining what they are, but just look at the figure. It's anti-correlated as a function, anti-correlated. The red curve and the blue curves are anti-correlated as a function of pi. This is what my student calculated for the same setup. This is for the topological Majorana zero modes, and you can see the same anti-correlation in the red and the blue. These are really the currents in the two hands of the interferometer. This is the robust and real bound states, and they give you exact similar signature. Nothing that you can qualitatively change. All right. So one thing you can do is you can do a real interferometric experiment where you include both Majorana zero modes. In this interferometry setup, they included only one Majorana bound state. The other one is over here. These are metallic rings. So we can do that. That's going to be a very hard experiment. Very hard experiment. And people are working on this, but it's very hard experiment. We propose a sanity check by doing a much simpler experiment. What is it? Two-terminal charge tunneling in just 2 minutes. This is well within the current experimental range, but somehow has not been done. So the idea is when these non-uniform or non-homogeneous potentials that are appearing, supposing they are appearing in the system, they are not going to be exactly symmetrical. They're going to be something like this or something like that near the two ends. Okay? Or it could be another like this. There is no reason for them to be reflection invariant along this plane in the most generic. So this is one setup for the two-terminal charge tunneling where the superconductor is isolated, and if you have tunneling from this lead to that lead through this Majorana-assisted electron transfer process, here you require charging energy and all that. This is another setup where you have a single electron charge tunneling where the charge comes from this metallic lead and the current is extracted through the superconductor. Here the superconductor is isolated and you are looking at the electron tunneling from here to there. Here there is no other lead here, and the lead to superconductor, the current is extracted through the superconductor. We are proposing a third setup where you have two terminal or two lead setup, but you do the experiment with one lead. So you collect data for bias potential to the left lead, the superconductor is grounded, but the right lead is isolated. So the current goes through this, but the right lead is isolated. And keeping everything about the experiment fixed, everything held fixed, you take another set of data where the bias potential is applied to the right lead, superconductor is grounded, and the left lead is isolated. Compare the data and correlate. What do you expect? Here again we have this asymmetric potential. This is the most generic case. And as you can notice, you have these robust unreal bound states coming down to zero energy much before this is topological. This is deep into the non-topological. Because remember, this is mu is like minus 4.3 delta, and these robust unreal states are happening at Zeeman field about 0.4, or it's about 0.4 delta. This value is is about of the order of 1 MeV. So yeah, so of the order of 1 MeV. And as you can see, therefore, the Zeeman field is much below or much smaller. I'm saying relative terms. It's smaller than the mu. So there's clearly in the non-topological case, but you have. So this condition is not. So this condition is satisfied. The topological condition where this should be a greater is not satisfied. So you have this robust low energy unreal bound states. This is for the other asymmetric. Now look at these calculated data. So you are looking at the correlation at the critical Zeeman field where the zero bias peak appears on the right lead and the left lead. And you see over here, the zero bias peak has appeared here. This is the Zeeman field and this is the energy. But of course, they are not correlated. That's what you expect. So of course, these inhomogeneous potentials are not symmetric. But there is actually more. You can see that, of course, the data here and the data here are asymmetric, but there is a symmetry set in above a certain value of the Zeeman field. And that's because the system is entering into the topological phase at that point. So the moment it enters into the topological phase, where gamma is greater than mu, or gamma is greater than square root mu square plus delta square is achieved, that's where the symmetry in the splitting correlations also set in. And you can see the same thing here. So this is you can clearly see that these zero bias peaks must be non-topological or robust unreal states because there is no symmetry between the two ends. It is above a certain value of the Zeeman field, symmetry sets in. And that's where the system has become topological. And for this configuration of potential, of course, there is no correlation between the two ends. So this is clearly in the non-topological robust unreal bound state. So if you have seen robust zero energy unreal bound state, and you have done the two-terminal charge conduction, two-terminal teleportation type experiment that Charlie Marcus's group did, you don't really know whether those are real Majorana zero modes or some robust low energy unreal bound states. This is what you can do. You can compare the sets of data from both ends. And if the splitting oscillations are correlated, like here, then you know that you have the systems in the topological regime, and you are actually probing Majorana zero modes. If the data is uncorrelated, you know that it must be because of low energy robust unreal. And the reason is obvious why that happens, because if you have Majorana zero modes, then it's only the two Majorana zero modes which perturb each other by overlap, and therefore, if you have a splitting oscillation on one side, you have the same splitting oscillation on the other side, the energy scale of the splitting oscillation. Not the visibility. The visibility of the splitting oscillations will of course be determined by what barrier potential you are applying at the two sides. But of course, you can make the barrier potential symmetric as well to get symmetric visibility. But even if the visibility is different, the scale, the energy scale at which you see the splitting oscillation, they should match. And that's the important point. And then you know that you are in the topological phase and you are looking at real Majorana zeros. So all three data sets are uncorrelated for robust unreal bound states. they become correlated above a certain Zeeman field. So that's my conclusion, that robust Runge bounces can be realized rather generically in these systems, in-orbit coupled nanowires. To realize truly non-abelian topologically protected Majorana zero modes, one has to solve a critical problem which you don't really know how to solve. They are now talking about the system being clean and so on and so forth, which was really a problem earlier, and that's where all those alternative scenarios came into the picture because of disorder induced. Now they're claiming the system to be clean, but we know that there are a large number of gate potentials, and they need to play around with the gate potentials to get into the zero bias conductance peak regime. So therefore, so this situation, you have to engineer hybrid structure with homogeneous active parts, no defects, no position dependent external fields, no interface disorder, etc. That is hard, and we don't really know whether you are in that region. In the absence of that, and short of an truly interferometric experiment, what you can immediately do within the current experimental capabilities, you take two-terminal charge tunneling as the most obvious smoking gun, well within experimental reach, and you can possibly conclude whether these objects that you are seeing are topological Majorana zero modes or some robust unreal bounces. With that,
thank you. We have time for two questions maybe. Yes.
How does the magnitude of the conductance in the ABS states compare to that in the Majorana zero?
Very good question. The magnitude of the conductance in the ABS state is not quantized to 2 square by h, but it can be 2 square by h. So the very fact that you got a 2 square by h peak does not tell you anything about whether it's an ABS state. Because in the ABS state, in the ideal case, when the two Majorana bounces are sitting on top of each other, you are expected to get a conductance of 4 square by h. But here you are physically separating. So depending on how strongly they are coupled, it could be 3 square by h, 2 square by h, 1 square by h, or it could be 2 square by h. So therefore, the common wisdom in the field that if you get a 2 square by h quantized peak, that must be Majorana zero mode, that's incorrect. And in fact, the most recent state of the art is people have found 2 square by h peaks, but that doesn't tell you anything about that. And that's true also for the Maryland picture that I mentioned. They have somewhat different calculation, but get the same. You can get a 2 square, but you don't really know whether these are robust unreal states or Majorana.
Any other question? Yeah, you can follow up.
Physically, in the ABS state, what's causing the separation of the two Majorana components?
So again, a very good question. So that's actually there are different ways to describe that. So you can think of this is something the referees are bothering us with, and this is not entirely correct, but in a first approximation, you can think of it like this. So you are applying this locally varying potential. Just think of the one that I gave the very first, the one which is up towards the end. So that means your effective chemical potential is changing in that region. So you can think of that region as producing a locally topological regime, where at the two ends you're producing Majorana bound states, which are strongly coupled by that because it's a short regime. Okay. So that's one way to look at it. Another way to look at it is you can actually show, as we did in that figure of the wave functions, that so if you have the very short localized potential, then you have an Andreev bound state, which is a conventional electrons. And you know the Majorana bound states can be thought of as half of conventional electrons, which means an Andreev bound state has two Majorana bound states coupled in itself. And you can show that if you somehow increase the width of this potential, you are separating them, and so it's like partially unfolded Andreev bound states. There is not much physical intuition there, except that this is something that you can actually show by doing calculation. And you can, if you are looking for a real physical interpretation, I don't have that at the moment, but Vaguely, you can think of it as a local short topological, which has its own problems.
So thank you, Sumanta, again, and let's couple this to thanking all the speakers today. Thank you.